Imagine solving a mystery, not with footprints or fingerprints, but with data. In this journey, we blend mathematics, imagination, and modern tools to uncover hidden patterns, sometimes from blurred clues, and sometimes from no clues at all. With the right approach, even the invisible can be estimated. And just like a detective prepares his magnifying glass before starting the case, we prepare our tool, MATLAB, ready to search through the evidence hidden in numbers. On a quiet, rain-soaked afternoon, Alex stumbles upon an old curious book, Sherlock Holmes, Mysteries Across Time. But this is no ordinary detective story. Written by a mathematician, it's a retelling of the Holmes adventures where mysteries are unravelled not just with intuition, but with logic, numbers, and mathematical insight. A tale that bridges centuries, showing how the puzzles of the past and the problems of today may be solved in strikingly similar ways. Outside, the rain taps gently on the window, each drop blurring the view like a fading clue in a mystery. Alex carefully turns the old pages, knowing they hold stories of the past and lessons for today. Alex's eyes fall on the heading, The Case of the Missing Heiress, the blurred clue. It feels like an invitation, not just to read a story, but to step into a problem-solving journey that stretches across time. Alex began reading the new mystery. In the story, Holmes notices an envelope on the floor, freshly slipped under the door. Inside is a brief, urgent note and a blurred, sepia-toned photograph, the only clue in the disappearance of a missing heiress. In the glow of the lamplight, faint outlines begin to appear: a church spire, an iron fence, and a part of a street name. With just a handful of clues, Holmes begins to reconstruct the scene. He doesn't need the full picture. By analysing what's known and how it's arranged, he estimates what's missing. In many ways, it's exactly what we do today with data. Holmes used landmarks. We use numbers. He saw beyond the visible, and that's the essence of interpolation and extrapolation, revealing the unseen from the known. For Holmes, the church spire was like a known point on a map. The iron fence was another. Piece by piece, these details helped him connect the picture, until the scene felt complete. In modern problem-solving, this is precisely the role of known data, the starting points from which we can logically extend and estimate the unknown. In that moment, Alex realised the connection. Holmes filling in the missing pieces of a photograph, and a data scientist filling in missing numbers in a data set. Both follow the same idea: start with what is known and let logic fill in what is missing. The story shifts from Holmes's adventure to a page rich with mathematical insight, a hidden layer of logic woven beneath the mystery. As Alex's eyes trace the page, he notices something striking. The author hasn't just described Holmes's reasoning, he has translated it into code. Right there, printed in the text, is MATLAB syntax, interp2. For someone new, it may just look strange. But put simply, interp2 is MATLAB's way of saying, take the values we know, spread out on a two-dimensional grid, and use them to estimate the values in between. The example begins with a matrix, a rectangular arrangement of numbers, just like pixels forming an image. In some cells, the numbers are missing. When parts of an image are missing, like blurred or damaged sections, the known values become anchors. Each missing value represented nan is a mystery waiting to be solved. MATLAB's interp2 function helps fill in the blanks. It analyzes the surrounding patterns and extends them across the missing spaces. With each interpolated value, the gaps are filled, not by guessing, but through logical estimation. And slowly, What was once blurred begins to take shape again. On the page, Alex sees side-by-side figures. On the left, a patchy, incomplete grid. On the right, a smooth, continuous surface where the gaps have been filled in. It's as if the photograph itself has been gently restored, the missing details, returning until the picture looks whole again. From the Holmes story, Alex realizes that data isn't just numbers, it's part of a story. And the weather outside isn't merely rainy, it's a riddle waiting to be solved. Let's join Alex as he dive into MATLAB, where patterns become pictures, and every question is a chance to uncover something new. Before solving mysteries, it helps to know your tools. MATLAB, short for Matrix Laboratory, is more than just software. It's where numbers turn into meaning, patterns reveal themselves, and logic becomes something you can see. MATLAB acts like a calculator, a graphing tool, and a logic engine, all at once. You don't need to be a programmer to begin. Just ask a question, enter your data, and let the patterns reveal themselves. Whether you're working with a set of temperature values or a blurry image or scattered data points, MATLAB helps you make sense of it all. When you first open MATLAB, it greets you with 4 main areas. The script editor, where you write and save your sequences of commands. It's like your detective's case file. Every step recorded, ready to be reviewed or repeated. The workspace. This is your evidence table. Here, every variable you've created is neatly listed with its name, size, and type. You can double-click to examine the contents closely, much like inspecting an item under a magnifying glass. The figure window, where your data becomes a picture. If 1,000 numbers feel overwhelming, a single plot can often tell the story at a glance. The command window, your direct line of communication with MATLAB. You type a command, you press enter, yes, and get an immediate response. Is like questioning a witness and getting answers in real time. Alex realizes that the strength of MATLAB lies in how smoothly everything works together. He can ask quick questions in the command window, write longer plans in the script editor, check his data in the workspace, and see the results in the figure window. Everything is connected, each part working together as part of the same investigation. Let's step into the world of MATLAB, where numbers come to life. Let's begin with a simple matrix. 4 sample points taken at regular intervals. These 4 measurements are the known data points. In MATLAB, they are stored in variables, like labeled containers that hold numbers. The first code simply means store the values 6, 9, 15, and 18 in a variable called x. These might be hours of the day. But for MATLAB, they're just numbers on a line, the known positions. Y holds the measurements at those x points. Using the plot command, MATLAB plots the data points as red circles. This initial plot is like looking at Holmes's photograph with only the visible details marked. It's not the full picture, but it's a clear starting point. The basic plot shows the data as dots. With the interp1 command, MATLAB connects the dots using straight lines, filling in the gaps. This process is called linear interpolation. Interp1 is MATLAB's way of saying, take the values we know, spread out along a single line, and use them to estimate the values in between. But what if the data isn't so rigid? With spline interpolation, we can trace a smooth curve, one that flows gently through every point. In just a few lines of code, MATLAB takes us from scattered numbers to a complete picture. This is where data becomes insight and where our journey into interpolation begins. Inspired by Holmes' method of connecting the dots, Alex begins looking at a mystery of his own, the changing temperature throughout the day. As the sun crosses the sky, Alex starts plotting what he knows, but the value at noon is missing, and that's when he remembers Holmes's method. and realizes he doesn't need every point. With the values he already has, he can estimate the missing one. This is where interpolation steps in, the mathematical way of estimating the unknown between values you do know. Alex begins setting up the problem in MATLAB. His dataset contains hours of the day and their corresponding temperatures. The missing noon temperature is what he wants to find. Alex turns it into a visual riddle. He can see exactly where the gap is, and MATLAB will soon fill it for him. Let's walk through the code Alex wrote. The script begins by entering the known data, times of day, and the corresponding temperature values. Think of these as the known fragments in Holmes's photograph. Next, he sets the point he wants to estimate. This tells MATLAB, "This is the time of day I'm curious about." The key command is interp1, the MATLAB function for one-dimensional interpolation. Hours, temperature are the known x and y data. Target hour is the x value where we want an estimate. Linear is the method used to interpolate. Alex uses MATLAB to estimate the missing temperature at noon, based on the data already recorded. At noon, the estimate comes out to 21 degrees Celsius. MATLAB's interp1 function calculates the estimated temperature at the target time. Next, Alex creates a range of time values using the linspace command. This command generates 200 evenly spaced points between 6 a.m. and 6 p.m. With these time points in hand, Alex calls interp1 again. This tells MATLAB to calculate the temperature at each of the 200 time values using linear interpolation between the known points. With just a few lines of code, MATLAB fills in the gaps. Alex begins with linear interpolation, connecting the known data with straight lines, a quick and simple way to estimate the missing values. Now it's time to visualize everything. Using the plot command, Alex brings the data to life. The red circles show the original measurements. A solid blue line traces the interpolated curve, and finally, a yellow square highlights the estimated temperature at 12 p.m., making it stand out clearly on the graph. But since temperature changes more gradually in nature, Alex tries spline interpolation instead. The curve becomes smoother, bending naturally between the points, offering a more realistic and accurate approximation. When MATLAB draws this, the gap at noon is gone, replaced by a value that fits perfectly with the surrounding data. Alex's curiosity doesn't stop at what he already measured. What happens after 6 p.m? This is where extrapolation comes in, using known data to estimate what lies beyond. Just as Holmes might wonder what lies beyond the edge of a photograph, Alex wonders what the temperature will be hours after his last recorded reading. In interpolation, we estimate values between known points, but in extrapolation, we push beyond them. It's a bolder step, because we're moving into the unknown without direct evidence. On Alex's plot, the data currently stops at 6 p.m. To go further, he'll have to extend the curve past that point. This is where MATLAB's extrap option comes in. When Alex activates it, the plot doesn't just stop, it projects the trend forward, using the pattern from the existing data. The concept is simple, but powerful. If you know how something has been changing, you can predict how it might continue. Alex turns to MATLAB once more. This time he's asking a different question, not what's missing between data points, but what might come after them. With a single line of code, MATLAB reaches beyond the last known value, predicting the temperature at 9 p.m. In interpolation, we fill the gaps between known measurements. In extrapolation, we step beyond the last known reading and extend the trend into the future. The target is set to 9 p.m. Using interp1, With the extrap option, MATLAB projects the temperature past the last known reading. A continuous range from 6 a.m. to 9 p.m. is generated, blending the interpolation region with the extrapolation. This is extrapolation, using past patterns to estimate what's next. Let's unpack Alex's code. The target hour is the question we want answered. Setting it to 21 directs MATLAB to estimate the temperature at 9 p.m. This is the key. Interpol1 is the 1D interpolation function, and with the extra argument extrap, it's allowed to continue the line, past the final data point. Hours, temperature are the known XY data. Target hour is point, where to estimate. Linear extends the trend with a straight line from the nearest segment. Extrap explicitly allows estimates outside the data range. At first, Alex uses linear extrapolation, extending the data trend with a straight line. For that, he creates a range of time values using the linspace command. This time, he generates 300 evenly spaced points, between 6 a.m. and 9 p.m. With these time points in hand, Alex calls interp1 again. This tells MATLAB to calculate the temperature at each of the 300 time values using linear interpolation between the known points. By keeping the original measurements visible as red circles, it is easy to tell exactly what was measured versus what is estimated. The blue line connects the dots in the known region and then continues beyond 6 p.m., making the extrapolation visually obvious. But to capture the natural variation more realistically, he switches to spline extrapolation. The result is a smoother curve that bends with the rhythm of the data, offering a better approximation of what might happen next. Alex may not have solved a Victorian case, but he discovered how the past inspires the present. Just like Holmes pieced together clues to reveal the truth, Alex now uses data, logic, and code to bring hidden patterns to light. What was once a mystery becomes data, and data a solution. From forecasting tomorrow's weather, to restoring lost pixels in an old photo, to predicting future trends in business or science, interpolation and extrapolation are everywhere. From Holmes's magnifying glass to MATLAB's command window, problem-solving evolves. Open MATLAB, load your data, try interpolation, predict, estimate, explore. Who knows what mysteries you'll solve? Thank you for watching.